All right, so welcome back everybody for today's session of the Cardiff Analysis Seminar. So the second to last for this academic year. Just a small reminder that on Thursday we have a special analysis plus applied seminar happening at 2 p.m. in person in the department. And if you can, you're all welcome to join. But for today, we have a regular online seminar, and we are pleased to have Michael Melgaard from the University of Sussex, who will talk about shining lights in the darkness, the mathematics of boson stars. So thank you very much for accepting our invitation, and over to you.
Well, thank you very much for the invitation. It's a pleasure to speak in this seminar series, and I actually intended to go to Cardiff, but then we have some logistic issues. So I couldn't actually make the trip. So today I'm going to, is it coming? Yes, it's coming, yes. So the topic of my talk today is actually a bit outside my normal activities. So since something around 2006, I have mostly pursued mathematical challenges in quantum chemistry. And I've investigated sort of two quite different research topics. And the first one of these is electronic structure models in quantum chemistry. As you know, one cannot solve the many particle Schrödinger equation when the number of particles goes beyond 5, 6 particles. And therefore, physicists and chemists have developed various approximations to the full quantum mechanical problem in their quest to determine the possible energy levels of atoms and molecules. And these approximations are divided into wave function methods like the Hartree-type method, which is central to everything in computational quantum chemistry, and density functional theories, where the main object is no longer the wave function, but the particle density. So it's all about reducing the underlying number of dimension of the problem. And the price paid when you go to these approximations is that you go from the linear Schrödinger equation to nonlinear PDEs. So the mathematics that enter here is, as I said, nonlinear PDEs, nonlinear analysis, critical point theory, calculus of variation, sometimes even differential geometry, spectral theory, and so on. So that's sort of the first of my activities. And the second is, it goes back to where I sort of started in spectral theory and scattering theory. So this is once again motivated by quantum chemistry. So it's about resonances or metastable states. So resonances is one of the few quantities which physicists and chemists can measure in their labs, and being able to localize them and compute them, at least approximately, is of immense importance. So the mathematics entering this area, as I said, is spectral and scattering theory of differential operators. And there's lots of sort of beautiful methods which enter this research: microlocal analysis, pseudo differential operator theory, semi-classical analysis, and so on. So all of the above concerns properties of ordinary matter, meaning atoms, molecules, people, planets, stars, and so on. So for ordinary matter, its basic constituents, the particles inside, all belong to the kind we call fermions, okay, which I'll talk a lot about today. Today, however, I thought it would be interesting to spend some time on matter which is not ordinary. So the topic is also triggered by very exciting developments in astronomy. So although this is not my area of expertise, some of the resulting PDEs are closely related to the ones I already mentioned, and the same applies to the methods we apply in order to settle fundamental questions like existence of solutions, like ground states, excited states, how many solutions, and so on. So let me just pick a few headlines I came across. So the first claiming, so this one is the first one, the first claiming that the universe could be littered with eerie transparent stars made entirely of bosons, not the fermions I mentioned before. So all particles we know belong to either the first category or the latter, right? And we do not know of any other category, okay? So in 2019, the world sort of collectively laid eyes on an actual image of a shadow of a black hole, the so-called M87 star. But the question quickly arose how we can be sure that it's a black hole and not a boson star. So similar to black holes, boson stars are predicted by general relativity, and they are able to grow to millions of solar masses, okay, and reach a very high compactness. And the fact that these share these features with, for instance, supermassive black holes led some scientists to propose that some of the supermassive compact objects located at the center of galaxies are actually boson stars. So here on this slide, you see this little extract from a paper from 2020 where Olivares and his team have calculated what a boson star might look like to one of our telescopes and how that would differ from a direct image of a creating black hole, okay? And so this is one example, and here's another example which concerns the so-called GW 190521, a short gravitational wave signal reported in 2020, which was initially interpreted as a quasi-circular merger of black holes, but later in an article by Bustillo and co-authors, the idea of what we're really looking at is the head-on collisions of two boson stars. And the latter is particularly exciting if confirmed, because it would also provide the first evidence for a long-sought dark matter particle. So let's just, at this moment, it's worth to bear in mind the current understanding of the contents of the universe. So here you have a pie chart that informs us that ordinary matter only constitutes something like 4.9% of the known universe. Dark matter is supposed to constitute 26.8%, and the even more mysterious dark matter is supposed to constitute 68.3% of the universe. So what is dark matter? Could it be these boson stars? And what is dark energy? Well, that's even harder question. But let's just pick out the beginning of the dark matter problem. So in 1933, Fritz Zwicky was the first, if I pronounce it correctly, was the first to use the virial theorem to infer the existence of unseen dark matter, describing it as dunkel materia. So galaxies in the so-called coma cluster were moving too rapidly, and he concluded it couldn't be stars, it doesn't shine, it's dark. So before I go more into this, I'll just remind you of a few things about stars like our own sun, okay? So stars shine, of course, because they are vast, continuous nuclear explosion, right? Nevertheless, the effect of attractive gravitational forces in such a huge body is not negligible, a fact that can be easily appreciated by noting that the sun maintains a spherical shape despite the nuclear violence in its interior. So the byproducts of the nuclear reactions are light, heat, and various kinds of particle, all of which produce an internal pressure that keeps the star expanded before these byproducts can leak out through the surface, okay? Now, after the nuclear reactions are finished in what we could call the post-twinkle phase, the star eventually cools, and it might be supposed that it would then collapse because of the gravitational attraction. Sometimes this does happen with great rapidity, resulting in what we know as a supernova, okay? The enormous gravitational energy is then converted into the production of a vast amount of light and numerous particles, mostly neutrinos. But sometimes the cold star, or the remnant of a supernova explosion, which is also a cold star, merely attains a new, much smaller radius and is quite stable, although lightless, all right? Of course, there's also a final, another final state of a supernova would be a black hole, in which the collapse might be silent or, well, invisible, because black holes do not permit light to escape. So now the question arises, so what is the determining factor for for total collapse or stability. And so that's the stellar mass, okay? The dividing line is several solar masses, okay? And the question is, what mechanism is available in the stable case to provide the internal pressure that prevents the gravitational attraction from crushing the cold star, okay? And the answer turns out to be the quantum mechanical energy of the constituents, fermions, normally. But actually, there are two kinds of cold stars. There's the neutron stars, and there's the white dwarf. So for instance, we are expecting our own sun to one day become a white dwarf. But I come back to the white dwarf later. So first, I want to say something about the neutron stars, okay? So the former kind, which are remnants of supernovae, are composed mostly of chargeless neutrons. Neutron stars were mentioned as a possibility, so now we're down here, by Landau in 32, after the discovery of the neutron by Chadwick in the same year. And in 1934, Barth and Zwicky proposed their connection with supernovae, and their actual existence was established by the 1968 discovery of pulsars, and later Gauss' identification of these as rotating neutron stars. So we will need Newton's gravitational formula, of course. So let me just remind you of this one. So here we have the coordinates x1 up to x capital N of capital N neutrons. And then the classical potential energy is given by Newton's gravitational formula, which is expressed here. So here we have introduced kappa as the gravitational constant g times the mass, the neutron mass squared here, all right? And the fact about these neutron stars are quite amazing. So first of all, their mass is a few solar masses, but the radius is only about 10 kilometers. So the gravitational force at their surface is about 10 to the power 12 times that on Earth. And the internal structure of such an object is hard to guess, because at these densities, right, especially the central density, neutrons will cease to look like individual particles and might become some sort of quark soup, all right? And moreover, this large mass in such a small volume will cause space to be curved in accordance with the principles of Einstein's general theory of relativity. Now, in the sequel, I will ignore these complications, and we shall suppose that a neutron star is just a collection of n particles with the gravitational potential energy, as you saw it on the previous slide. And I want to focus on what we will call the Chandrasekhar model for neutron stars. But before doing so, and because I was not entirely sure who's in the audience, I thought it's worth to just provide a little ultra short description of the theory of quantum mechanics before we carry on, and maybe point out a few things which you don't usually hear in let's say a course on quantum mechanics. So the state of a particle is a complex valued function psi, so-called wave function in L2, satisfying the normalization condition, which is given here. So modulus square of the wave function integrated over the whole space equals 1. And Born's interpretation is that this modulus square is the probability density for finding, let's say, an electron, the particle at x, okay? And so if we're given a state psi naught at time 0, then the state at time t later, psi of t would be given by a u of t time acting on psi naught. So u of t here is a strongly continuous one parameter group of unitary operators on L2. I notice I switched to RD in general, which is better, of course, than 3. And Stone's theorem then says that u of t is actually given as an exponential function raised to the power minus it times h, where h is a self-adjoint operator on this L2 space. And this is referred to as the Hamilton operator of the system. And now in non-relativistic quantum mechanics, the Hamilton operator is typically the closure of essentially self-adjoint differential operator, roughly of this type here, where you have a kinetic part here describing the kinetic energy of the particle, and you have a potential VFX, real valued potential. And if it's non-relativistic, we refer to that H as a Schrödinger operator. So for instance, if you think of a molecule, let's say you have M nuclei and you have N electrons, then after you separate out the motion of the nuclei, I mean, they're so heavy that you can regard them as fixed. So this is the Born-Oppenheimer approximation. Yeah, then you would have a Hamiltonian, the electronic Hamiltonian described by this operator here. So again, you recognize this as the kinetic energy of the N electrons. Here you have the attractive energy between the electrons and the nuclei, and here you have the repulsive energy between the electron-electron, okay? So that's just an example of Hamiltonian. Now, if we start out in a state psi naught, which belongs to the domain of H, yeah, then our evolution psi of t, given by this, is strongly differentiable and obeys a differential equation, which is given here. So this is the time-dependent Schrödinger operator equation, okay? Which of course goes back to Schrödinger, and this is also what he got the Nobel Prize for, deriving this wave equation in 1933. By the way, shared with Dirac for his contributions. Now, if you take a Schrödinger operator H, like we've seen, it describes the energy of the system. And if the particle is in a state psi, then the expectation of the energy equals this expression here. So this is, as you recognize, this is an inner product of psi and H acting on psi in L2, okay? And in a similar way, the multiplication operator, like VFX, for instance, or the differential operator P equal to minus I times nabla, describe the position and the momentum of the particle, respectively. And the expectation of the kinetic energy would then come out as the inner product of, and now I didn't introduce H naught here, but H naught was this part here, okay? This part here. Yeah, then you can compute the expectation of the kinetic energy by performing this calculation here, okay? All right. So the motion of quantum, so quantum mechanics determines the motion of particles, and the allowed quantum states, like, you know, think of the electrons orbiting the nuclei, yeah, they're determined by the time-independent Schrödinger equation, which is an eigenvalue equation of this type here, okay? So, of course, in an undergraduate module on quantum mechanics, you would see the cases we can actually solve in closed form, like the harmonic oscillator, where you take VFX equal to this potential here. And here you see the corresponding solutions. So here you have psi, here you have modulus square of psi for this particular case. So, of course, if we go back to the origin of quantum mechanics, it was invented because it was necessary to understand atoms and molecules, and in particular, it was necessary to come up with a new theory which could explain the stability. For instance, hydrogen, right? Why is hydrogen stable? Why does, I mean, from Newton's classical mechanics, this hydrogen should essentially collapse, right? And when you, for instance, take a first module on quantum mechanics, then you often go away with the impression that it's Heisenberg's uncertainty principle, which is enough to explain stability. This turns out not to be true for many particle systems, and the so-called Pauli principle, which I'm going to mention in a moment, plays a decisive role. But first, let's just recall what Heisenberg's uncertainty principle says. So here's Heisenberg In fact, there are three gentlemen here we need to introduce, because I'm going to give you three versions of the uncertainty principle. So coming back to hydrogen, when the electron is close to the nucleus, its kinetic energy, which could be zero classically, is forced to increase in such a way that the total energy tends to infinity as the average distance x goes to zero, right? And so usually you see this equation in physics that the difference in x times the difference in momentum is bigger than or equal to h bar. But here mathematically, we can write Heisenberg's uncertainty principle. It's by this inequality here. Okay, so notice the x square here, and you have the inverse here. But there are two other versions which sort of in the more refined study, mathematical study of why matter is stable, for instance, it turns out that it's actually inequality of this type, Sobolev inequality, which is more important in this version here. Okay, so that's why I'm pointing these out here. Okay, because they will always, these inequalities will always enter in a decisive way in these kind of studies. Okay, so I mentioned at the beginning of this talk that all particles in the universe can be divided into these two categories, bosons and fermions. And so indistinguishable particles in nature come in these two types, bosons and fermions. And the bosons have permutation symmetric wave functions, whereas the fermions, so here, for instance, let's say we have the n particles, and let's say it's electrons, which is a fermion. So if we interchange the position of two electrons, then it would generate a minus in front of the wave function. So this would be an antisymmetric wave function, and that's the kind of condition the fermions obey, whereas the other one don't. Okay, the bosons. So if one neglects interactions among the particles, the wave function is just a symmetrized product of functions like this, with psi k appearing nk times, say, and for fermions, nk is 0 or 1. So that would be the Pauli exclusion principle. So you often hear physicists or chemists say that in each orbital, there's at most two electrons corresponding to spin up and spin down. Okay, but for bosons, nk could be 0, 1 up to capital N. So here's an illustration, right? So there's basically there's a limitation for the fermions, but there's no limitation for the bosons. Okay, and since we are talking bosons, we better mention that bosons obey the Bose-Einstein statistics. So here's a picture of Bose. And let's just also, because we are talking about these two categories, so let's take a quick glance at the standard model of particle physics to see how all known particles are distributed into these two categories. So here you see on the left-hand side, you have the fermions. Okay, so you have quarks here, you have the electron, and over here you have the bosons. So Higgs, for instance, have spin 0. These guys here all have spin 1. Yeah, and all these fermions have a half integer spin, I should mention. Yeah, but anyway, you see everything is divided into these two categories. So we have discussed a little bit the neutron stars, but now let's return to the second kind of cold star, the white dwarf. And the Chandrasekhar limit is the maximum mass of a stable white dwarf star. Okay, so the currently accepted value of the Chandrasekhar limit is about 1.2 solar masses. So white dwarfs resist gravitational collapse primarily through electron degeneracy pressure, compared to main sequence stars which resist collapse due to thermal pressure. Okay, so the Chandrasekhar limit is the mass above which the electron pressure in the star's cores is insufficient to balance the star's own gravitational self-attraction, okay? So consequently, a white dwarf with a mass greater than the limit is subject to further gravitational collapse, and this could then evolve into a different type of stellar remnant, such as a neutron star or a black hole, okay? So those with masses up to the limit remain stable as white dwarfs. And this is, for instance, what we expect when it comes to the fate of our own sun, okay? That it stays stable as a white dwarf when it runs out of hydrogen fuel, yeah? Okay, so now let's look at the Chandrasekhar model, which, well, that's the name I'm going to use about this. And let's talk about first the Hamiltonian. So in fact, I'm going to discuss simultaneously fermions and bosons, okay? But here's the Hamiltonian. So you see there's a kinetic part, but it looks a bit different from before. Before we had the negative Laplacian, right? But here it comes as the square root of the negative Laplacian plus m squared. We come back to that. And then we have the Newton's gravitational potential energy here, yeah? And then of course the Hamiltonian has to act on these underlying Hilbert spaces. And we have already discussed that it has to be the antisymmetric space for the fermions and the symmetrized version for the bosons, okay? Here I also allow, well, yeah, Q here. This is the freedom of spin, and M is the mass either of the neutron or the boson, depending on what we're looking at. And now I see I have called Newton's gravitational constant small g. Before it was capital G, but it shouldn't cause too much confusion. So this is still kappa equal to g times m squared. So you have this attractive energy potential here. And of course, what we're interested in is to say something about the ground state energy, all right? So we define this as the infimum, and now we come back to the expectation value of the energy. So here it is. That's just the inner product of psi n and Hn acting on psi n, as psi n varies over the Hilbert space, always normalized to 1. And now it turns out that if n, the number of particles, is strictly bigger than the Chandrasekhar limit, yeah, then no ground states exist, and the energy goes to minus infinity. So that's and the limit comes out like this for fermions. So you have tau c. This is some number, of course, which we can't actually. Well, yeah, that one we can determine, yes. But the one below omega c, we can only estimate from above and below. But anyway, this is the basic fact about the ground state energy. And let's just before we continue with summarizing the results on this model here, let me just say a little bit about this term here. So it comes from Einstein's special theory of relativity. So if the particles move very fast, we have to take into account special relativity. And if you do that, then you will get exactly this Klein-Gordon operator for the kinetic energy, okay, according to Einstein's theory. And the standard Schrödinger operator, meaning the negative Laplacian, right, it doesn't obey the invariance principle of special relativity because its derivation originates from Newton's mechanics. In contrast, if you take the Dirac operator, it will obey the principle, but unfortunately the Dirac operator is not semi-bounded, so you wouldn't have a traditional variational principle, but you have for this one. So this is the nice thing about choosing this expression, and you would have to choose, you would have to take into account relativity, because the particles in a place with such a high density, they would move very fast, right? So v, the velocity over the the speed of light is not small. Okay, so this is why you ended up with this one. Okay, and this goes. So here's a picture of Klein. It turns out it's impossible to find a picture of Gordon for some reason. But what is worth to point out about this one, and here I write it slightly different, where you have the speed of light, c explicitly here. Okay, so you can see how it comes in. Everywhere else I put it equal to 1. Okay, but it's a non-local operator. Okay, so it's not like the differential operator and minus Laplacian, right, which is local. And it's a first order pseudo differential operator. And since I mentioned Hardy and Sobolev before and indicated that these inequalities are important when you study stability and things like that, then I just want to phrase them also in this relativistic setting. Okay, so they come out like this for the square root of the negative Laplacian. Okay, and one more thing I need to say before I can actually formulate things rigorously later on is that we need some relativistic variational spaces. And the key thing we need to know about is this space here, the Sobolev space of order ½ which is just defined as the functions in L2 for which the Fourier transform times this weight belongs to L2. So this is the Fourier transform. And then when you have this one, you can then introduce the corresponding antisymmetric and symmetrized spaces in the usual way. All right, so back to the summary of, sorry, I was here. Back to the summary of what is known about this Chandrasekhar model. So here I focus on this period of time first, okay? We have already mentioned Chandrasekhar himself, we mentioned Landau, and one of the first studies of self-gravitating scalar bosons can be found in this paper from '69 by Ruffini and Bonassola. And bosonic matter is analyzed by Messer and also by Thiering. Thiering discusses bosonic black holes. And in these papers, it is argued that the Chandrasekhar limit for boson stars is approximately the mass of a mountain, okay? So, and moreover, the intuitive scaling ideas used by Messer and Thiering are turned into rigorous statements in a paper by Lieb and Thiering in '84. So you see here, in this paper, they show that the Hamiltonian we've been talking about is bounded below if n is more than or equal to some constant times kappa to the power -1 for bosons, and bounded below if n is more than or equal to another constant kappa to the power -3/2 for fermions, okay? And they also show that it's unbounded below, so unstable, if these relations hold, okay? And in fact, it is conjectured in this paper from '84 that the ground state energy of n bosonic particles with relativistic kinetic energy, I mean this pseudo-relativistic kinetic energy, is given by the minimum of the pseudo-relativistic Hartree energy functional in the mean field limit. I'm coming to this in a moment and I'll write everything out on the slides, okay? But that conjecture was then later, '87, confirmed. So it was established by Lieb and Yao. So the Chandrasekhar, respectively, Hartree-type equations are exactly correct as n goes to infinity, g goes to 0 for all values of g times n to the power 2 or 3, respectively g times n. And I will state the theorem in a moment, okay? I just want to mention that, of course, Lieb and Thiering I just mentioned, I mean, they are famous for their proof of stability of ordinary matter, which is from around 1975. Originally, it was proven in the late '60s by Leonard and Dyson, but Lieb and Thiering came up with a whole new proof, which was much more elegant and much closer connected to the physics, so one could really understand what was going on in the proof, whereas Dyson Leonard's proof was, you know, sort of a series of, let's say, inequalities, and it was, yeah, it was more brute force, where and their proof, Lieb and Turing, is also much shorter, right? Yeah, so let's just state this theorem by Lieb and Yao from 87. So you see here, you fix tau as kappa times this n2/3, smaller than this critical value, and then their theorem for the fermions say that when you look at the quantum energy divided by n, the number of particles, and you let n go to infinity, it equals exactly this infimum here, okay, where you see you have introduced an energy functional of this type here, okay. So this is the fermion version, and now, and this is the one we're going to focus on, of course. If you look at the bosons and you fix omega as kappa times n, so not 2/3 now, but just n, and it should be smaller than some number omega c, yeah, then the same limit tends to this, okay? And here you have the Hartree energy functional, which comes out like this, okay? Here you recognize the the kinetic energy term, and here you recognize the sort of Hartree term, yeah? Also, it turns out this one equals minus infinity if tau is bigger than tau c, and likewise this one equals. So you have instability, right? You have collapse if the two parameters is bigger than the critical values, right? And if you then derive the corresponding Euler-Lagrange equation for this functional, then you get the pseudo-relativistic or semi-relativistic nonlinear Hartree equation, which we're going to talk about in a moment. So this is the result by Lieb and Turing from 87, and let's just try to understand why we should choose, why this omega equal to kappa times n is the crucial parameter for bosons and not this one, okay? So for bosons, we might imagine that as a simple product function of this type here, where you take some non-negative psi in L2, so then you compute the density as n times modulus square of this phi. Did I say psi? I meant phi, sorry. And if you then compute the kinetic expectation value of the kinetic energy and the potential energy, then it takes this form here for the kinetic part, and you come out with this for the potential, okay? So if you then add these up while you make n, this is a heuristic argument, right? You make n large, right? Then you get the Hartree-type functional, which popped up in the paper by Lieb and Yao. Well, it was conjectured already by Lieb and Turing, yeah? And then you introduce the corresponding Hartree energy, and then if you scale, so if you you scale like this from, you replace rho by n times rho, and you take kappa to kappa times n, and e to n times e to n times e. Yeah, then you can see that you come out with this as the crucial parameter for the bosons, and not n to the power 2/3, which is fundamental for the fermions. All right. So now we are getting closer to the paper I want to present. Okay. So the pseudo-relativistic Hartree equation is the nonlinear evolution equation given by this. All right. So this equation describes a system of these gravitating bosonic particles in a regime where effects of special relativity are important because the particles are close to the speed of light, but retardation effects and space-time curvature can be neglected, okay? In fact, Melgaard and his line proved that 2 emerges as the correct evolution equation for the mean field dynamics of many body quantum systems modeling pseudo-relativistic boson stars. We don't really need the V here in what I'm going to tell you, so, but otherwise it would be in modeling other stars, okay, if it's present. So let me summarize the results for this kind of equation, okay? So so there's a series of work by Fröhlich and co-workers, okay? Starting with, for instance, blow up of solutions of these nonlinear wave equations with Hartree-type nonlinearities, existence of boosted ground states or solitary states, waves for the pseudo-relativistic Hartree equation, well-posedness, and also long-time behavior of solution initially close to a boosted ground state, and even uniqueness of the ground state. And the result I want to present is sort of fits into this, because we have managed to show with a different approach existence of these boosted ground states, but also existence of excited states. All right, so this is a paper with one of my former PhD students. All right, so let me just, I see time is actually moving faster than expected, yes. Well, maybe, yeah, okay, so let me summarize some of these results I just mentioned. So with the help of the conserved quantities of charge and energy, so here you have n of phi, and here you have the energy potential functional, which you recognize again. And then you can show well-posedness. So explicitly, you can show that if you have an initial state in h1/2, so the space we introduced previously, there exists a unique solution phi belonging to this space here, okay? And moreover, one has global in time existence under this kind of condition here, right? And NC is bigger than 4/pi, okay? So this is a universal constant. Now, due to the focusing nature of the nonlinearity in our equation 2, which was here, yeah, there exist solitary wave solutions. So meaning you have solutions of this type here for some, so here you have a constant mu, and you have this phi of x belonging to this space. So this is defined as the minimizer of the energy potential subject to this constraint here, okay? And any such minimizer is a ground state and satisfy the corresponding Euler-Lagrange equation, which would be this one here, yeah? So notice in the paper by Lieb and Yao in '87, they proved existence of ground states under this condition here, okay? Based on rearrangement inequalities that allow one to restrict one's attention to radial functions, which simplifies the variational calculus. Now, to extend existence to so-called boosted ground states, and what does that mean? It means that here up here in 5, instead of x, you replace by x minus v times t, and then in doing so, it requires an additional term in 6 of this type here. So I v dot nabla acting on, well, times phi, yeah. And so this was started by Fröhlich and his team, and they were using Lyon's concentration compactness to show existence, okay? And they also started blow up, and they found that if they start from a spherical symmetric initial state, phi naught, c naught infinity, satisfying this kind of bound, this would lead to blow up of phi in finite time. So in other words, we would have this for some capital T, some finite time, yeah? And now this condition implies the smallness of this one, that this cannot hold, okay? So in physical terms, finite time blow up of phi of t is indicative of gravitational collapse of our Boson star, and we can then regard this constant nc as the Chandrasekhar limit mass, okay? All right, so if we consider these boosted states, so solutions of this form, where we just, so lambda here is just a real number, and we have some traveling velocity v smaller than 1. So remember, I put c equal to 1, right? So this is c. Now, solutions of this kind cannot be directly obtained from solitary waves at rest. You know, if you take v equal to 0, and then you do a Lorentz boost, because our equation 2 is not Lorentz covariant, okay? So to bypass this obstacle, instead we insert this ansatz into our equation, and it will give us an equation of this type here, okay? And so we get this term, this extra term appears, right? And the corresponding energy there, or sorry, the associated minimization problem would then be the original energy functional plus this part here, okay? And this we now denote by EV of phi, okay? And of course we still have the constraints as before, yeah? So for these solitary waves, Fröhlich, Jonsson, and Lenzmann in 2005 showed that there exist solutions to this problem, okay? So they proved that under these conditions here, we recognize this one again, yeah, then you have a minimizer, so you have a boosted ground state, and it satisfies this Euler-Lagrange equation, okay? And if n is bigger than or equal to this critical n, yeah, then no minimizer exists for the problem, okay? Here's a diagram where you can see how you can split. So here you have energy, right? And here you have n. So n along the x, e along the y-axis. So in region 1, all solutions are global in time, and the unboosted ground states are minimizers of the functional E subject to this bound. And if n exceeds nc, yeah, then the energy can attain values below -½ m times n. And as shown in Fröhlich-Lenzmann 99, for the spherically symmetric initial states that belong to region 3, we have in fact blow up in finite time, okay? And finally, the qualitative behavior solutions with initial conditions in region 2, so we are up here now, in this region, appear to be of indefinite nature. All right, so I mentioned this theorem, but I can see now I don't have time to discuss it, so let me just skip that. But I did mention Melgaard and Slein before, and briefly said what they managed to prove. But anyway, all this work sparked the idea of trying to see whether we could somehow show existence of excited states to this for this problem. And so here I'm just writing up the problem again. But here I introduce an admissible set of functions, so we called it Mn, okay? So it's just the functions in h½ under this constraint. But Mn is important, okay, now. So what we have managed to prove is that under the usual conditions, there exists a positive constant Nc, depending only on V, such that, again, under this usual condition, every minimizing sequence of the equation of the minimization problem here is relatively compact on Mn up to translations, okay? In particular, there exists a minimizer of EV on the admissible sets, which satisfy the corresponding Euler-Lagrange equation and also the constraint, okay? But more than that, so this was just the boosted ground state, but more than that, we can show there exists a sequence of distinct solutions of this problem. So that would be what we call the excited states, okay? So we can show existence of that too for Lagrange multipliers lambda k, and we can also say something about these Lagrange multipliers. Now the question is, how do we prove this? Because Fröhlich and Lenzmann and Jonsson used concentration compactness, and I have a little comment here. So we note that radially symmetric solutions do not exist for this, because if phi was radial, the left-hand side of this equation is radial. However, the right-hand side takes this form here. So that's only possible. So it's radial if and only if phi prime is identical to 0, okay? But now we are, I mean, for this, we're looking for non-minimal solutions, right? So how do we go about this? So we are going to use a method which was developed by Lyons. And of course, he has many significant contributions in PDEs, right? But in 87, he wrote a paper on the Hartree-Fock equations, where he not only sort of cleaned up Lieb and Simon's original proof of existence of solutions, but he also provided another method. And this other method was later streamlined in work by Gusub and Fang. And the main scheme of proof goes like this. So the main steps is, first of all, to show existence of almost critical min-max sequence, and then use information on the first and second derivatives of the sequence to prove that Lagrange multipliers cannot tend to 0. And then eventually prove relative compactness, okay? So I just, if I have time, I don't know whether I have time, but it seems it took a little longer than I expected. But I want to say a little bit about the first steps here and sort of the framework of Lyon's method, okay? So for a C2 functional J on a Riemannian manifold X, a sequence Hj is said to be a Paley-Smale sequence at level L and of order less than m whenever these conditions hold. So first of all, J of Hj should tend to a limit L. The first derivatives should go to 0. And thirdly, there exists a sequence of real numbers tending to 0 such that for every J, the Hessian has at most m eigenvalues below minus delta J, okay? And we say that it satisfies a Paley-Smale condition at level L and of order less than m, provided it's relatively compact in the manifold X, okay? And then the framework for the critical point theory. Well, it looks a bit heavy, right? But so I'll just read through it, right? So suppose G is a compact Lie group acting freely differentiable on a complete C2 Riemannian manifold X. And we take our energy functional, it needs to be a G invariant C2 functional on X with first and second order derivatives being Hölder continuous on X. And we suppose that upright H is a G homotopic family of dimension K. So that means we have something like this, where S here is a fixed G invariant compact subset of Rk, and the continuous functions here. So yeah, what is this? This is the set of all G equivariant continuous function H from S into our manifold, okay? Then Fang and Gusub, and this was around 93, proved this theorem, which is sort of the abstract version of what Lyons did in 87. So if you consider these min-max levels, then for any min-max sequence in this H we introduced on the previous slide, and any K, there exist sequences Xj in X and delta J in R tending to 0, this one, such that this sequence is a Paley-Smale sequence at level L and of order less than K. So in our case, of course, we take our J as our EV functional. Our manifold is this Mn, yeah? We take G as Z2 and S as the unit sphere in the Euclidean space. And then we consider the following homotopic classes of order K. So we introduce HK like this for odd continuous H from here into Mn. And the mean max levels are then defined like this. I mean, similar to what you saw in the previous theorem, right? The abstract theorem. And to make this work, one of the things we need to show is that the Lagrange multipliers cannot tend to 0. So always with these kind of problems about stability, you you always run into some kind of electrostatic balancing act, and here in the form of a lower spectral bound. So so under these conditions, and here this one comes in explicitly, right? You need that for each integer k, there's a delta, such that the unique self-adjoint operator associated with this differential expression admits at least k eigenvalues strictly below minus delta. So so this is a result that enters here. And then the main, and this is the last thing, the main proposition in order to actually prove the theorem I showed you is to prove a proposition like this, that if you take a sequence phi j in our Mn, a sequence that satisfies the Paley-Smale condition at level L and of order less than n, yeah, then and for some sequence of positive reals tending to 0, the following three conditions hold, and these are the ones I mentioned before, right? Yeah, then any sequence satisfying these three conditions is relatively compact in our admissible set up to translation, and moreover the limit satisfies the Hartree-type equation here. Okay, so so this is this ends my little sketch of the proof of the theorem I presented, and this was this is work with my, as I said, with my former PhD student, who was a so-called sandwich student at Uppsala University and his home university in Burkina Faso. So that's Frederic Sungo. So thank you very much, and sorry for running a little bit of, well, a bit over time. Yes, sorry for that.
Thank you very much. So any questions for the speaker?
Yeah, I have a question about, so you showed the existence of this ground state and the excited states. So is there, and you said they can't be spherically symmetric, right? So, but can one say anything about what they look like, the structure of these excited states?
Well, this is not, yeah, well, at this moment in time, I cannot say anything about that. No. Yeah. Actually, preparing for this talk, I came, you know, I was just checking whether any new results appeared, and I can see that there's quite a bit of activity about this equation, and there's some new papers, but I don't think none of them is addressing what you just asked, but there's definitely new papers I didn't know about which have popped up in the last year.
It seems that whenever you have this equation which you're looking at here with the I don't know whether it's due to the non-linear, sorry, to the non-local kinetic energy, but maybe also this non-linearity, right, with this self-interaction basically with its own density. So you can't have simply structured solutions. Is that correct? You can't have anything which is just which you can easily write down, but they will always be kind of complicated in their geometry.
Sorry.
Yeah, sorry. So, I mean, it's yeah, maybe that wasn't a clear question. So it's but so if you instead of the Klein-Gordon kinetic energy, you had just the Schrödinger energy, let's say.
Yeah.
And then, but still this self-interacting term with the convolution as a nonlinear term. So in that case, one still can't get simply structured ground state or excited states. Is that correct? Maybe you didn't look into that.
Well, I probably looked into it a long time ago, but yeah. You know, I would have to check. I don't dare to just. There might be some results actually. Yeah. But I would. Yeah. I can't remember now.
Yeah, because I mean, a long time ago, I tried something like this, just trying to find a simply structured solution for this. And then I mean, I just moved on to other things because I had the impression that there's a minimum complexity which you need to put in order to write down any kind of solution. But okay. Yeah. And then I have one more question actually, but it's more a physical question, which I was wondering about this with the boson stars, because massive bosons, as far as I know, they're all very short-lived normally, right? So they don't exist for a long time. So how can a boson star exist in that sense? I mean, of course, that's not what you looked at, because you looked at just the interaction between them.
Yes. In fact, yeah. I mean, if you do go into sort of the more physics literature, then you will also realize that, I mean, the model I'm looking at is too simple, right? And you would have to go to general relativity, and then you would actually be looking at something quite different.
I see.
Yeah.
So maybe they're actually, it's also more like a quark soup, only of a different description. Not quark, but yeah, boson. Yeah, boson soup. But well.
Yeah.
It could be that they stabilize each other somehow, right?
Yeah, I don't even know what the status is, because I was essentially preparing this talk in December 21, the first time around, and at that point, so the articles I mentioned in the very beginning, I don't know what the current state of affairs is, whether there's some kind of better understanding of these things now, but I mean, it's quite exciting stuff.
Yeah. It seems very new, actually.
Yeah, there's some very nice talks about it you can find on by some of these authors I mentioned. Yeah. But the models they're looking at is not the one I'm looking at, right? Because they're looking at the most simple, because this is something we can actually do something about.
Yeah, sure. Yeah, thank you.
Further questions for the speaker? So if that's not the case, let's thank Michael again for the nice talk.
Sure, yeah.